Good evening, everyone. So we further go on with the Applied Optics online courses, the series. And in last few classes, we already covered the parts about the sources, basic principles of LED characterizations, application of various current of kind of LEDs. And before we go into laser, I thought it'd be good to quickly finish the photodetectors. Now, a few of this acknowledgement and the list of books we should be studying for this course. Now, this part is about the physical principle, how photodetectors work, the type of photodetectors like PIN, APTs, their characteristics like quantum efficiency and responsivity, noise, response time, and structures. So basically, photodetectors are optoelectronic devices to convert the optical signal back into electrical impulse. The light detector are commonly made of semiconductor material. When the light strikes the light detector, a current is produced in the external circuit proportional intensity of the incident light. In simple, I'd say it's just a reverse bias PN junction. When you strike it with a photon, it creates electron and holes and it creates a current, and that is what is used to change its some physical property. Most of the times it's resistance, and that is used for the detection. Now, optical signal generally is weakened and distorted when it emerges from the end of fiber, like fiber optics. The photodetector, that is why, needs to have this kind of performance requirement. It needs to have a high sensitivity to the emission wavelength range of the received light signal, a minimum addition of noise. So we need to have minimum noise. It needs to be fast in response to and speed to handle the desired data rate, insensitive to temperature variation, compatible with the physical dimensions of the fiber. So we are talking about a detector which is just after a fiber optics. It needs to be reusable, like it should be with a reasonable cost compared to the system components, and it should have a long operating lifetime. Now, some of the important parameters that we need to be knowing is quantum efficiency. It is the ratio of the primary electron hole pairs compared to the incident photon to the photon incident on the diode material. Detector responsivity is the ratio of the output current to the input optical power. Hence, this is the efficiency of the device. The spectral response range, this is the range of wavelength over which the device will operate. I assume these are the most important parameters of the photodetectors that we should be knowing very carefully. The noise characterizations. So the level of noise produced in the device is critical to its operation at low level of input light. Response time. It is the measure of how quickly the detector can respond to the variety of input light intensity. Now, the type of light detectors we generally have are PIN photodetectors and avalanche photodetectors. And the materials which are used for photodetection, there are many of them depending on their energy gap and the cutoff wavelength. Wavelength range for the operations: silicon, germanium, gallium arsenide, indium gallium arsenide, and indium gallium arsenide phosphide. So indium gallium arsenide is used most commonly for both long wavelength PIN and avalanche photodetectors. The physical principle of photodetectors, particularly for PIN photodetectors, the device structure consists of P and N semiconductor regions separated by a very lightly endowed intrinsic region, the I region. In normal operation, a reverse bias voltage is applied across the device so that no free electron or hole exists in the intrinsic region. Incident photons having energy greater than or equal to the bandgap energy of the semiconductor material give up its energy and excite an electron from the valence band to the conduction band. So there's a structure, typical circuit diagram of a PIN photodetector. The high electric field present in the depletion region causes a photo-generated carrier to be separated and be collected across the reverse bias junction that gives rise to a current flow in the external circuit known as photodetector. In PIN photodetector, the photocarriers, basically incident photon generates free mobile electron-hole pairs in intrinsic region, the I region. These charge carriers are known as photocarriers since they are generated by photon. The photocurrent is given by the electric field across the device causes the photocarriers to be swiped out of the intrinsic region, thereby giving rise to a current flow in an external circuit. This current flow is known as the photocurrent. Now the energy band diagram of a PIN photodiode looks something like this. You can clearly see that the photon here, which is more with more energy than the band gap, hits and generates this kind of like electron hole pairs within the depletion region. In a PIN photodetector, an incident photon is able to boost an electron to the conduction band only if it has an energy that is greater than or equal to the band gap energy. Beyond a certain wavelength, the light will not be absorbed by the material since the wavelength of the photon is inversely proportional to the energy. Thus, a particular semiconductor material can be only used over a limit of wavelength region. The upper wavelength, that is the cutoff wavelength, is determined by the bandgap energy, Eg, of the material. As the charge carrier flow through the material, some of them recombine and disappear. The charge carrier move a distance Ln or Lp for the electron and hole before recombining. This distance is known as the diffusion band. Now, the time taken to recombine is like the lifetime, which is tau n or tau p respectively. We have discussed about this one before also. So that is the relationship of the diffusion length and the recombination time. And we are having another parameter here, was diffusion coefficient. Now the photocurrent, to understand it, like as a photon flux penetrates through the semiconductor, it will be absorbed. If PIN is the optical power falling on the optical photodetector and x is equal to 0, then Px is the power level at a distance x into the material. Then the incremental change will be given by this, where this is the photon absorption coefficient at a wavelength lambda. So basically, now we have the power in terms of the distance x within the material with term of, so it's basically an exponential relationship with the P incident. And we also have to take care of the photon absorption coefficient. Now this can be written in the form like this also, that the optical power absorbed Px in the depletion region can be written in terms of the incident power here. So here it's not I, it's EO. And the absorption coefficient strongly depends on the wavelength. So the upper wavelength cutoff for any semiconductor can be determined by its energy gap as follows. Taking entrance phase reflectivity into consideration, the absorption power in the wave width of the depletion region becomes like this. See, if you plot it with respect to wavelength, the optical absorption coefficient for, for some of this material like gallium arsenide, germanium, silicon. Now, responsivity, as I mentioned before, is a very important parameter for a detector, for a photon detector. The primary photocurrent resulting from the absorption is this. The quantum efficiency we have defined before is basically the number of electrons minus the whole photo-generated pairs and the number of incident photons. So it's something like this. Whereas the responsivity is the IP to P0. So if we draw responsivity to wavelength for various materials, we get something like this. A typical PIN pin diode schematic is given here, which includes an anti-reflection coating, electrical contacts, the I layer, N and P layers. The generic operating parameters for indium gallium arsenide pin photodetectors are given here. So the parameters to understand are wavelength range, responsivity, dark current, rise time, bandwidth, and bias voltages. If we move to an avalanche photodetector, photodiode, ETs are internally multiply the primary photocurrent before it enters the following circuitry. In order to carrier multiplication take place, the photo-generated carriers must transverse along a high field region. In this region, photo-generated electrons and holes gain enough energy to ionize bond electrons in valence band upon colliding with them. This multiplication is known as impact ionization. The newly created carriers in the presence of the high electric field result in more ionization called avalanche effect. For avalanche photodetectors, photodiodes, if you think about the ionization range, the average number of electron-hole pairs created by the carrier per unit distance traveled is called the ionization range. Most materials exhibit different electron ionization rates, alpha, and hole ionization rates, beta. So the ratio between beta and alpha of the two ionization rates is a measure of the photodetector performance. Only silicon has a significant difference between electron and hole ionization ranges. If we think about the responsivity for APDs, the multiplication factor current gain M for all carriers generated in the photodetector is defined by this, where IM is the average value of the total multiplied output current, and IP is the primary photocurrent. The responsivity of APDs can be calculated by considering the current gain as this. The current gain versus the voltage for different optical wavelengths are given here. The generic operating parameters like we discussed for the other one also. For indium gallium arsenide, avalanche photodetectors are mentioned here. The noise calculation is also important for photodetectors. The detection of weak optical signal requires that the photodetector and its following amplification circuitry be optimized for a desired signal to noise ratio. It is the noise current which determines the minimum optical power level that can be detected. This minimum detectable optical power defines the sensitivity of the photodetector. It is the optical power that generates a photocurrent with the amplitude equal to that of the total noise current. So S by N is basically given by the signal output from the photocurrent and photodetector's noise power plus the amplifier's noise. I won't get into too much of detail for this signal calculation. Noise sources are sort of important because sometimes you need to discuss where the noise is coming from. The principal noises associated with the photodetectors are the quantum or short noises, arises from the statistical nature of production and collection of photogenerated electrons upon optical illumination. It has been shown that these statistics follow a Poisson's process. A dark current noise in the current that continues to flow through the bias circuit in the absence of the light. This is combination of bulk dark current, which is due to thermally generated E and H in the PN junction, and the surface dark current due to the surface defects, bias voltage and surface area. In order to calculate the total noise present in the photodetector, we should sum up the root mean square of each noise current by assumption that these are uncorrelated. The total photodetector noise current is equal to the quantum noise current plus the bulk dark current noise plus the surface current noise. You can further calculate these noises, be that useful, SNN. Now, you need to have an idea about the detector response time. The response time for a photodetector together with its output circuit depends mainly on the following three factors: the transit time of the photocarriers in the depletion region, the diffusion time of the photocarriers generated outside the depletion region, the RC time constant of the photodetector and its associated circuits. So the response time of a photodetector, if we think it through, the response time of photodetectors with its output circuit depends mainly these three factors: the transient time of the photocarriers in the depletion region, the transient time depends on the carrier's drift velocity, and the depletion region width. So it can be given by this: the diffusion time of the photocarriers outside the depletion region, and the RC time constant of the circuit, which we mentioned in the last page. The circuit after the photodetectors act like RC low pass filter with the pass band given by this. So the photodiode parameters responsible for these three factors, transient time, diffusion time, RC time is constant, are absorption coefficient, depletion region width, photodiode junction and package capacitance, amplifier capacitance, detector load resistance, amplifier input resistance, photodiode series resistance. The diffusion process are slow compared to the drift carriers. In a high field region, to have high speed photodetectors, the photo carriers should be generated in the depletion region and close to the depletion region. The diffusion time should be less than or equal to the carrier drift times. The effect of a long diffusion time can be seen by considering the photodiode response time. The response time is described by the rise time and the fall time of the photodetector inputs when the detector is illuminated by the step input of optical radiation. The rise time is typically measured from 10 to 90% of the points, the leading edge of the output pulse. For fully depleted photodiodes, the rise time and the fall time are generally the same. They can be different and low bias levels where the photodetector is fully depleted. For fast carriers, the charge carriers produced in the depletion region are separated and collected quickly. For slow carriers, electron hole pairs generated in the N and P regions must slowly diffuse to the depletion region before they can be separated and collected. We'd rather focus on the structure of indium gallium arsenide APT. Separate absorption and multiplication, SAM kind of structure is given here. In indium gallium arsenide APT superlattice structure, the multiplication region is composed of several layers: indium, aluminum, gallium arsenide, quantum wall separated by indium aluminum arsenide barrier layers. The temperature effect of the abalone decaying is also given here. Now, if we do some comparison between various kind of photodetectors from various materials like silicon, germanium, and something interesting to find out.